see the slideshow view of the topic for today, for the lecture 4?
Yes.
Okay. All right. So today we are going to continue from where we left last week. So we were studying, discussing about shaft joints. Now we are going to continue that. A bit elaborate. So, and we make calculation of von Mises stresses on a shaft.
Thomas, sorry for interrupting you, but now we see the present view.
Okay, so you see the presenter view. Okay, just a second. Thanks for noting me. How about now?
Yeah, perfect. Thank you.
Excellent. So the learning target for today would be to learn more about shaft joints in general. We learn about other types of shaft joints, friction shaft joints, which can be done either by compression or interference, and something general about glued or welded or soldered joints, and also about a flange joint. Okay, so apart from the key joint that we learned last time, there are also other methods for joining shafts together, and one of the most used, especially for the larger diameter shafts, is friction. And the reason is that as we learned in the lecture of the key joints, a key joint is not that good when we have a big diameter shaft and the torque is very high, because there is a physical limitation to the diameter, to the size of the key and the key slot, and that cannot increase in the same order as the diameter of the shaft increases. As you probably know, the torque resistance of a shaft is proportional to the diameter in power of 3, which means that when the diameter is increased when the diameter is doubled, it means that the torque resistance basically is 8-fold. And the key joint and the key slot and the key strength properties cannot match this high increase in the torque in the higher diameter shafts. So therefore, for the higher torques and for bigger diameters, it's usually done with the friction joint methods. And the friction is provided through compression. So the joining parts are being compressed together, and this compression and friction prevents sliding. And also, while doing this, we get the benefit that we can also prevent loosening or clearance in the joint. So there's no backlash movement in the cases of bidirectional or fluctuating loads. And generally, we have 2 options through which we can obtain the compression in the joint. First one is the so-called interference fit, which means that we provide the compression by tolerances. And by tolerances, it means that when we have a shaft to hub joint, the shaft is originally slightly larger than the bore of the hub. And therefore, when we force these two together, there will be a compression in between. So the shaft is a bit bigger in diameter than the hole where it's supposed to be attached. And when we, by one or another, we put these together, we have a compression. Another option to provide the compression would be a pure mechanical compression. So that we can obtain, for example, by using taper collar, as is presented in the picture. Picture here, you can see there's this red part is a tapered collar around the shaft. And when we tighten this collar axially against the outer sleeve, we also obtain the compression to the shaft, and therefore we have a friction joint. And also there's a possibility that we have simple halves of a shaft, like in the lower picture. This is very simple, inexpensive type of clamp coupling, and in here we can provide the compression by just tightening the screws. But when we have bigger diameters in demanding applications, there is usually either interference fit or this kind of taper collar solution. And the consideration we have to think when we design a joint like this is how to assemble it, and possibly how to disassemble it. If we have to disassemble the shaft multiple times, then this kind of taper collar or screw compression joint would be better. Because if we have an interference fit, which is forced together by using a cylinder or by heating the components, it's much more difficult to dismantle it. And also the assembly is more difficult. Also, we have to consider the loosening. Is there a possibility that due to the fluctuation of the loads, the compression could be somehow minimized over time? So what kind of safety margin we will need for the compression to sustain for the whole lifetime of the component. Stresses due to thermal variation, especially when we are doing interference fit, which sometimes, as we learn later on, interference fit is assembled using heat. So we are heating the hub to be bigger so we can put the shaft inside. And that will work okay when both and the shaft and the hub are in the same temperature in the operation. But if we have a situation in the operation conditions that the hub could be, for some reason, be heated up to be of higher temperature than the shaft, that would mean that the compression would diminish due to the temperature difference. That is something which needs to be taken into account in the designing of the joint. Possible leaks, corrosion, because we have a contacting surfaces, there is a fretting corrosion possibility. That is in some conditions something we need to consider, and fatigue always. In here you can see some examples, practical applications of friction joints. So here in this left picture there's a I don't know actually what is the device in the hub, some flange or probably just connecting the shafts. Seems fairly big in diameter compared to the brick sizes in the wall behind. So obviously it seems that the hub in the center it's somewhat heated because there's brownish color in it, and the shaft hulls have been cooled down, and we can see it from the frost. Also, if you take a normal angle grinder and you put a blade on it, it's a friction joint. You tighten it, and the torque from the angle grinder is transferred through the friction between the bolt and between the shaft of the angle grinder. And by the way, I don't see chat messages right now. If you have anything to ask or say, please do. But say it out loud so I can hear it. I only have a chance every now and then go to see the chat. So now I was seeing that. What is the device at the right bottom? You mean this one? This one over here. This is just a compression coupling. So this is a device that can be used to couple two shafts through compression joint. So we have 4 pieces of Allen key screws that can be used to tighten the sleeve onto the shafts. So just used for connecting 2 shafts together. Okay. Then we go a bit more deeply into interference fit joint. So as we learned, interference means that the hub, this blue piece over here, is a hub bore is smaller than the shaft external diameter. So when the shaft is bigger in diameter than the hole in the hub, we will have interference, which means that when these components are at rest in same temperature, they would be basically overlapping. But when we forcefully attach these components together, the hub hole will stretch out, and this shaft will of course compress, shrink down. And this is very common method for joining components in mechanical engineering, but it's used for mainly circular components. However, it is possible to use interference fit joint also for other forms. They can be octagonal or even square, but most often it's used for circular objects. And the reason is that by when we machine a circular object, a shaft or a hole for a hub, we can more easily control the tolerances of the manufacturer. Typical components which are attached with this kind of joint is, for example, different kinds of gear wheels, pulleys, impellers, sleeves, rolling bearings. In many cases are attached with the interference fit. Rotors and, as we learned, also couplings are being attached using this. And the characteristic of interference fit is that it's typically load carrying through tolerances. However, it can be sometimes used only for centering. So this when there's a very mild interference, so mild that it doesn't actually carry any load, but it just centers the components to each other. So that is one of the benefits of the interference fit. It will characteristically it will provide the centering function for the components. Also, there is a benefit that it can provide a torque limiting function, so action as a fuse. But when doing that, it's the designing and the dimensioning of the tolerances and the surface roughnesses and everything has to be quite precisely done. It is not so easy to manufacture this kind of joint so that you could get precise torque limiting. However, it's possible. And another drawback is that if you are using interference fit joint as a torque limiting, it usually means that if there is over torque and it will slide, it will destroy the surfaces. So it means that probably the original nominal torque capacity is not achieved anymore after the slipping. So we have a hub which has a bore of smaller diameter than the shaft. So we had to do something special to assemble these. We can do the hub heating, and by hub heating we can increase the diameter of the hole to make them assemble together. And we can do that by in a small simple cases just by heat gun, or if we have a induction heater, that would be a bit more precise. The component, the hub, can be put into oven if there is a sufficiently big oven available, and in some cases we can use a gas flame, which is not in many cases it's not the most practical way because you had to have a quite good setup to be sure that you will heat up the component evenly in the circumferential or the perimeter of the component. So using just gas flame from one side and moving the torch around will not provide even heating for the component. But there are methods and sort of jigs which can be used for this. So there could be, for example, a gas flame setting from all directions for the component, and using that kind of device we can get somewhat even heating for the component. Or we can use cooling for the shaft. We can, in simple cases, we can just use cold spray. We can get some degrees of Celsius minus by the cold spray for small components. It's not very practical for bigger components because you would need quite a lot of cans of the cold spray. We can put the component in freezer if the component is small enough. But when there's more minus degrees required and the component is bigger, it's usually done with dry ice. And in most severe cases, it could be that even liquid nitrogen is used, so we can get more cooling. And if the interference is very heavy, so there's a very big difference in the diameters of the shaft and the hub bore, we can even use both the heating and the cooling, and it will be needed. So here in the pictures below, we can see what kind of pressure distribution we can obtain by this interference fit. When we have a cylindrical components, it's of course quite even, as we can see. And if we have a shaft which has a hole inside, we can see the distribution as shown here in the picture. In this right-hand side picture, we have a coupling of an electric motor, fairly big electric motor, megawatt class, I would say, and there they have a motor coupling which is attached with a interference fit joint, and they are using hydraulic jack to install and take out the coupling side.
Excuse me.
Yes.
I have questions like if in the case heavy interference joint, so the shaft is cooling to minus temperature and the hub is heating up to some high temperature, and when we push it together, is there any harmful to the component because they like instantly change the temperature really fast?
That is a good question. When installing this kind of component, when we have both cooling and heating, it has to be done quickly, because otherwise, if there is when we put this cold and hot component close to each other, they start to level the temperatures. So the cold component will start to warm, and the warm components start to cool down, and that will happen pretty fast, of course. So therefore, there is only limited time space for installing this component, and if it's if the temperature difference is going down too soon and the component isn't at its correct place, it could be that it's attached to an incorrect place, and it's possible that you cannot anymore take it away. And that's actually been happening in my previous career. We had a large electric motor which had a stator inside. Stator is the sort of iron core of the motor, and the stator was attached to the frame of the machine with the interference fit joint, and the interference was quite heavy. It was sufficient to carry all the short circuit load of the electric motor, something like 50,000 Newton meters. And of course, the stator was circular in outside diameter, and the frame inside was circular as well. And in the frame there was an opening for the cables from the stator, electric cables, at one side, but not on the other side. So it meant that the stator had to be put into the frame in exactly correct position so that we could get the cables out. And unfortunately, it happened one time that there was a inexperienced crew who was doing the installation work, and they put the stator inside the frame in incorrect position, 180 degrees apart, so that the connection cables were at wrong side of the frame. So there was no opening in the frame for the cables at that side. And it went in, and it had time to cool a bit, not completely cool down, but cool a bit, so that there was a grip available when it was noticed that, okay, now it went wrong, we had to fix it. And it was tried to dismantle, even though it wasn't completely cooled down. It was impossible to take it out. So basically the only option was to break the frame from outside, so cut the frame into pieces to get at least the stator to be used for the next frame. So it wouldn't have been possible to force the stator out from the frame in one piece using brute force. So the installation process is quite delicate, I would say, in interference joints.
And if the hub is cooling down too fast, too quickly, so the surface of the hub will be like martensite, become martensite, and it will be really hard and really easy to crack. So is there any solution, or it completely doesn't harmful to the component?
Yeah, you are right. If we heat up the hub too much, a steel hub, so that it will be on austenitic region, and then we cool it down very rapidly, then it would harden. But usually these components are not heated up that hot, because we want to keep the original material properties in the hub. So usually the maximum temperature that is used for the hub is around for steels around 300 degrees of Celsius, just to make sure that the original material properties are not changed, and therefore there would be no martensite in the crystal grain structure.
Yes, thank you.
And for the others to know, if you didn't know what we were talking about, martensite is the type of the steel grain structure which is very hard, and that is usually desired when we do a hardening, quenching, and tempering for a steel component. That is the hard crystal grain structure we want to have it, but we don't want to have it in these cases where we want to keep the original material properties for the components.
You mentioned that 300 degrees for steel structures is about the highest temperature, but what is the lowest temperature? Because as I understand it, you can use liquid nitrogen, but I think we'd also want to avoid cold cracking. So what is the lowest recommended temperature?
Actually, I've never found one, and the reason is that steel itself, if you don't heat it, it will last very low temperatures. I would say minus 200, no problem with that, but just don't hit while it's cold. So if you are giving the steel an impact when it's cold, then it might crack, but just as itself, resting in cold shouldn't harm the microstructure.
Okay, thank you.
Okay, So now when we have the interference fit joint, there are few factors that affect to the capacity of the joint. Of course, the dimensions, meaning the diameter and length of the joint. Surface quality has effect. Would somebody maybe guess how would the surface quality affect to the torque capacity of the joint? Surface quality in the mating surfaces.
Would a higher level of coarseness increase the torque? And like if it has a fine polished surface, you'd have, well, less torque because there'd be less friction.
Yes, that would be exactly that was the answer I was expecting, because that's the one everyone would estimate. But actually it's vice versa, because, and the reason is that when we have a coarse surface, there will, and we have high compression attached, there will be a smoothening effect for these, so to say, rough high peaks of the surface. And therefore it will actually reduce the torque capacity. We can see it later when we do the calculation according to DIN standard for this kind of compression joint. So in the equation, if you have a higher RZ value, it will actually reduce the obtained torque capacity. But that is of course due to the nature of compression. So when we have this high compression, it will cause this leveling of the rough profiles. But of course, if we have a normal two pieces just resting to each other without very high compression, it's quite natural that the more rough surface will give more friction. Okay, so of course then we have tolerances which do affect to the torque capacity. So what is the amount of interference we are obtaining? And cleanliness, that is something which has a quite high effect on the torque capacity. So there shall be no dust, no rust, no grease, nothing in between, so that the calculation values would be achieved. In Finland, there's a standard SFS 5595, which has been used for calculation of interference fit joints. You students, you have ability to access the SFS Standardization Society web page through our library's web page. So there's a link, an online link to the SFS web page, and you can find that standard from there. So if you wish to see it, that is completely in Finnish, of course, but then the relevant international standard is DIN 7190. Unfortunately, our library does not have access to DIN standards, so therefore I've been translating this calculation procedure to the slides, and you can see the equations in there. And now we could
sorry.
check.
Yeah. Where was the link for the Finnish standard? Is it on the machine elements page, or is it in one of the slides?
It's not, I don't have the link here, because you had to go to the LAB library pages and log in with your own account, and then you can find in the databases, you can find the SFS online service available. It's not, if I would put the link over here, it wouldn't work, because you would have to log into the library pages with your own account.
Okay, thank you.
Okay, and now we could check the couple of videos. Please comment if you can when I started, if you can hear the sound. So if you don't, then I will try to do something about it. Do you hear the sound as well?
Yes,
Yeah.
Good. Okay, here you can see that there's a shaft which has been cooled down, and now they are lowering it onto the kiln trunnion. They don't have that much time to put it, and you can see that there's a shoulder in the shaft which is used to position the shaft in correct place. So that is the best possibility when you are using interference fit, so that you have a clear place where you can just drop down the components and they will set up into the correct position.
Little tiny bit south, yeah. There you go. That looks pretty good there, Al.
That's good.
Yeah, once
And
it
one
starts going, you'll be
important
going.
thing regarding this
Yeah.
kind of joint type is, of course, that you have to heat components, you have to cool them down, and both are quite dangerous. So if you put your finger onto the cold shaft, you will immediately get damages. As you can see, they have this kind of cardboard wrapping around where they can touch more safely. And there it is. And when it stays
I went
for some minutes, then it's practically impossible to take it away in one part. Let's take another one. Here we have a hydraulic mounting of a taper sleeve. There's no sound in here, so we just use this kind of hydraulic nut where we can attach pressure into it, and there's a piston which is pushing the taper collar to position the bearing correctly. Let's take it again. The good side of this method is that if we would have this kind of tapered inner bore bearing, and we would like to install it just by using a normal shaft nut, which is tightened onto the shaft. Why would that be a little bit not so good option as this one?
Could you please repeat what option with nuts? So what exactly we should do with it?
So if now we can see that in here we have this piston which is pushing the inner raceway to its position. But if we would do this so that instead of this hydraulic device we would have a shaft nut, because here is a thread, so we could attach a nut around here and just tighten the nut, and that would do the same thing. But why would it be not so good option?
Maybe because the shape of the shaft is in conical shape. Well, it's conical shape, and the distance we can push the collar will be dramatically different from what we can do with the pistons.
Mm-hmm. Yeah. Is there anyone who has been sometimes installing a shaft nut onto the shaft, thread on a shaft? No one.
Yes, but I'm not sure what the answer. I'm not sure what the answer is here, but yes, I have done that before.
Okay. Do you remember how it was done?
Vaguely. Yeah, I really am not sure what the answer is, but if I have to be honest, yes, I have done this before.
Okay, so if you have done this with a normal shaft nut, you probably know that it's been tightened by hammer. So there's this kind of a lever tool, tightening tool for shaft nut, and then you just hammer it to get the nut tight enough. And that is no way precise enough for a bearing like this, because then you would easily over tighten it. Here, as we can see, then when the cylinder is advancing, there is the clearance between the rolling elements and the raceway will reduce. And by this kind of method, we can quite precisely tighten the inner raceway so that we get a correct clearance between the raceway and the rolling elements. If we would do that with a shaft nut and hammering, with a hammering tool, probably we would make it too tight so that we could make this clearance to go zero, and that would not be good for the lifetime for the bearing. So it's, first of all, you don't need to use brute force here when using this kind of hydraulic device. Another more important benefit is that you get much more precise clearance setting for the bearing. Yeah. Then there's still one. This is about. Yep.
Sorry for interrupting. The difference only in precision then?
Yes, basically.
Okay, thank you.
Here is a SKF Marine coupling for 2 shafts. So this kind of this is basically just a steel collar, but there are cavities which can be filled with pressurized oil, and therefore making it much more easy to assemble and disassemble this kind of joint. If we would do this type of collar onto 2 shafts, so here you can see the division line. So there's shaft number 1, maybe input, and there's the output side here. If we would do this just with a shrink fit, so meaning that we would heat up this collar and then press it against to these shaft hulls, then it would be more or less not possible to dismantle it. But when applying this kind of hydraulic coupling, we can introduce hydraulic pressure into the mating surface, and that makes it possible to take these components apart again if needed. So here we can see that there's the surface is being filled with the pressurized oil, and then we can move the collar freely on the oil film. Okay. Anyone been using that kind of devices? No one. Okay, but if you write in the YouTube interference fit and assembly, you can get multiple more nice videos about how to perform assembly, and also some not so good assembly processes. Also, you can find the videos about when something gets wrong and the components are oriented in incorrect fashion. But like every joint and every technical thing, each of them the limitations, also interference fit joint. The downsides are, of course, that you will need the heating and cooling tools, possibly substances and safety equipment. It's not always, if you need very low temperatures or very high temperatures, the equipment for safe using of those might not be that affordable. Also, disassembly on the site conditions could be challenging, as we learned. If we have a pure normal interference fit joint done with a temperature difference, it could be that it is merely impossible to take it apart in the site. And if you can take them apart, the reassembly after disassembly could be impossible to do for example, to damage to the surface. Of course, that is not the case when we are using, for example, this SKF system of hydrostatic pressure. But with a normal type of interference fit joint installed with the heating and on the temperature difference, that would be possible. And also, if we don't have a proper positioning accuracy provided by shaft shoulder null, it could be that our component is positioned in a incorrect position on the shaft. So when we are using interference fit joint, always remember to use positioning shoulders, like for example here in this picture of a bearing system where we had the bearings pressed against a shoulder. So here it is quite safe to use interference fit joint between the inner raceway and the shaft, because we have a shoulder against which we can press the bearing, and we can be sure that it's in exactly in the right position. But in this case, only interference is not enough, because if we would do this kind of bearing system, and there would be only interference fit between the shaft and the inner raceway, and there would be no shaft nut here, there would be a phenomenon that when we put a heated bearing onto the cooled shaft, and when these temperatures are leveled, there is possible that there will be a small clearance between the journal and the inner raceway, even though initially we put these faces together. But because there is a reduce in temperature in the bearing raceway and increase in the temperature in the shaft, there is possible that there's a small gap after the temperatures has been leveled. So therefore it's important that when we install it, we introduce continuous pressure through the shaft nut, which will keep the bearing in contact with the shaft shoulder. So then it will not introduce the clearance between the inner raceway and the shaft shoulder. Okay, then another form of shaft joint is glued joints. One might consider that it's not that state-of-the-art method, but yeah, maybe not. But in some cases, it's quite practical way of attaching components to the shaft. And the good side of this joint type is that the clearance between the parts is not a problem. Actually, it is required. You need to have some kind of clearance so that you can have a gap for the glue to enter. And also it can be used to remove the clearance. In the maintenance operations, it's sometimes been used if, for example, a shaft is very worn out and there's material missing and it's not anymore in the original diameter. We can use glue to sort of repair and fill the gap that is present. The good side is also that it will increase the joint flexibility. because glue is never as stiff as steel. And also it will provide torque limiting function. And from this point of view, it's better than the interference fit joint, because if the glue is breaking due to the over torque, then usually the components are not destroyed from surface. There are, of course, a residue of the old glue that has to be removed, surface cleaned again, but probably you are able to use the components again and assemble the components again. Typically, this kind of method is used for lightly loaded pulleys, small pulleys, gear wheels, maybe repairing of damaged joints also in bigger diameters, and removal of clearance in case needed. And some cases it can be used for locking bearing raceways. If there's for example, too loose fit for outer raceway of a bearing, glue can be used to attach the outer raceway to the housing to prevent it from rotating. And it's of course very simple method. But there are also drawbacks in the glue joint. One of the major drawbacks is that in order to have a defined strength for the joint, you have to have an even distribution of the glue. So of course there would need to be a uniform layer of the glue over the whole surface. And it's not always so easy to provide that, especially if you consider that you have a shaft of 200 millimeters in diameter and the joint length would be maybe 150 millimeters. It's not that easy to make sure that each place in the joint is filled with the glue. The glue joint strength depends on the dimensions, of course, the length and the diameter, but also the glue type, and it depends on the thickness of the glue in the layer. And typically in a way that if the thinner the layer is, the stronger the bond is. But it is also so that if it's very thin, it's not that flexible. If you increase the thickness of the glue layer, you will get less strength, but you will increase the flexibility. And if our interference fit joint was very, how to say, subtle or very sensitive to the surface cleanliness, glue joint is even more. So the surfaces need to be very clean, no rust, dust or grease. And also the strength of the glue joint is depending on the temperature. Not only the temperature on the operation, higher temperatures usually tend to lower the strength of the polymers, which is the cured glue or dried glue. It can be considered as a polymer. So when it's in a high temperature, the strength is less. But also in a way that if you apply the glue in, for example, very low temperatures, it could be that it doesn't cure, or it will take a lot of time to cure, or you will need some agents that will speed up the curing, some activators to make the glue to dry or cure in the cold temperatures as well. So therefore, low temperatures during assembly could be problematic, but also high temperatures, because if you have very high temperature, usually the curing time is shorter. So it could be that short that it's you don't have enough time to prepare the joint. And dismantling on the site conditions could be sometimes also difficult. And reassembling is limited. There is a possibility to reassemble the components in the glue joint. You can take them apart. Usually the glue breaks, but limited means that if you take these components apart, you have to make sure the surfaces are being cleaned. So if you want to put them together, you have to carefully take away all the residue of the old glue before applying new one. Okay, now I'll just fix one typo here. There's a lot of questions in the chat. I didn't know that. Please use voice when asking the questions, because I really can't see the questions while I'm presenting. There's a question about, are there material limitations for larger interference fit joints? Well, yes and no. Basically, you could do the interference fit joint of any material, but of course, if it is like wood, it doesn't make sense. But any kind of steels could be used. Any kind of you could say that any kind of metals can be used for interference fit joints. And you don't need to consider them for this course. In the project, let's see if I'll put the interference fit calculation view. Probably not. Probably it will be something else. And the question about how about the interference fit limit? How large can it be? Maybe Sun, can you briefly explain a bit more? What do you mean? Do you mean that how hot we can heat up the components, or?
Yes. I mean that, like, what is the limit for to heating and cooling those materials together? Like, is there any limit for like the format with heat to make interference fit?
Yeah, there is of course a limit for each material. As I mentioned, the standard defines for steel that it should be below 300 degrees, but there are of course steels that can sustain higher temperatures without any damage to the microstructure. For some materials it could be lower. For example, aluminum couldn't take even 300 degrees. For bronze it would be lower. For plastic, of course, lower. Some special alloys like 50% of nickel content super steels, they usually can sustain very high temperatures and could be heated up to maybe even 400 to 500 degrees without no problem. So it depends on the material.
Okay, I understand.
Excuse me.
Yes.
About the temperature gradient, would the temperature gradient, if it is too large, would damage the material? Like the difference between temperature between the hub and the shaft.
That is something that needs to be calculated through the interference fit calculation, so that we don't. If I understood correctly, you mean that if we introduce too high interference, there will be tensile stress, which is too much for the material. Did I understand correctly?
No, I mean the difference between two temperature. Like the hub is too hot and the shaft is too cold. When they hit each other, will the material be damaged?
Yeah, if I did understand correctly your question, it's in my opinion that wouldn't harm the components if we just keep in mind the material limits. So if the difference between the hub and shaft temperature is high, then it just makes the assembly more easy. But of course, there's a limit from the material, so the material cannot be heated to too high temperature or to too cold temperature, depending on.
Yes. Yes, thank you.
Okay.
So there is a presenter view again. Okay, thanks.
Yeah. It's seems that it's always opening the presenter view on the Moodle for some reason. Okay, but thanks for noting me. Please let me know if you see something strange, because I can't see my own view. How is it presented in the Moodle? Okay, then one more type of a joint which can be used. It's welding and soldering. In Finland, in Finnish, we could sometimes say that we use Kemppi glue. So that refers to the welding machine manufacturer Kemppi. So welding joint is a Kemppi glue joint. And when we are doing a shaft joint with the welding or soldering, it's especially with welding, it's usually not that state-of-the-art method. So it can be sometimes used, but it's not the best. And the reason is that when we weld, we usually introduce heat, so much heat to the components that the materials will melt, and that's a lot. And as a result of that, it will cause residual stresses to the components, which is not something we want. But if the requirements for the component for the lifetime or the deformations are not that high, it could be that it's possible to use. And but when it's been done, it's usually some method which will introduce as little as possible heat. So it could be like electron beam welding or laser welding, so that this joint would not be heated too much, and the deformations would stay in low level. And soldering is always an option, and the difference between the welding and soldering is that in welding, the base material always melts, but in the soldering, the base components do not melt. Only the material to be filled, the soldering material, will melt. And therefore, when the attached components do not melt, it will introduce less deformation, less residual stresses than welding. But the downside is that the joint strength is, of course, a bit lower compared to welded, and to some extent the process of soldering, so that the solder would be filling the gap all over. A bit same like a problem as we had with the glue. So that is the downside of the soldering. But in some cases, sometimes it been used, like in the picture. There's a small pinion of a bevel gear, and it's been welded on the shaft. Okay, then one more type of shaft joint, which is it's basically in between. Is it a shaft joint or is it a coupling? You could say that this kind of a piece that you can see over here, you could say that this is a coupling. It's a flange coupling basically. But these flanges can be also introduced directly onto the shaft. So this flange form can be forged onto the shaft, and then it's more or less a shaft joint. And the good side of this flange joint is that there are numerous standards for these flanges. So there are standards for size portfolio for different torques: SA-EDIN, Japanese JIS, SAFS. And due to the reason that they've been standardized, they are fairly inexpensive. And of course, it's quite easy to decouple. You just take out the screws and pull the key away, and that's it. And you don't need much axial space for doing that. They can be used for torque limiting function if we introduce a brake bolt or torque limiting bolt into the holes. And there's also different possibility to attach to the different kind of parts. It could be another flange, it could be a coupling, it could be some flexible or isolating element, which is the counterpart. The drawback of this kind of design is that it is, if we want to have it completely clearance-free, it's not that easy to design. And also it's difficult to design as self-centering. We can introduce some interference into this bore of the flange, which will then provide self-centering, but then it's not anymore as easy to assemble. But these are widely used in various applications: gearboxes, Cardan shafts, vessel propeller drivelines, electric motors. Always, quite often they have this kind of flanges, agriculture and machinery, conveyors. And here in the lower picture you can see example of a very large driveline. I think it was taken from some power plant, and there's a Cardan shaft which is fairly big, and it's been done with the flange joints. Okay, this was all about the theory, and next we can move on to the shrink fit calculation. So in here I have presented a calculation procedure, how to perform it according to SFS 5595, which is based on DIN 7190, and onto the method of known interference or known tolerances. So it's applying the shafted 3.2.2 of SFS 5595. There are also other methods for defining the interference, but this calculation procedure is when we know the tolerances, how we can calculate the torque capacity. And the task would be to calculate what is either minimum and maximum torque capacity of this kind of shaft to hub joint. So nominal diameter of the shaft and the hub bore is 44.5 millimeters, and there is some tolerancing, which is now H6 and R7. And due to these tolerances, we will have a difference in the diameters, and that is in the range. So there's range of difference in diameters, and you had to calculate what is the range. And according to that, you will have minimum and maximum torque transfer capacity. Did you already have tolerances in Simo Sinkko's machine design lectures this week?
We did.
You did. Okay, so you know how to calculate H6 and R7.
Yeah, pretty well. Either using
Okay.
SolidWorks or standard or online calculators.
Okay, yeah. And in addition to calculate the minimum maximum torque, you will need to calculate what is the needed heating temperature in order to assemble the hub onto the shaft. So considering that our shaft would be in room temperature, you would need to calculate how hot the hub needs to be so that we can assemble it onto the shaft with no problem. Let us consider the material would be 355, and all surfaces are cleaned from dirt and grease. They are clean and pure, and we can do the heating process in oven. And the surface roughness for both the shaft and both the hub bore is RA 1.6. And in the next slides, I have shown you the process how to do it, and there are some necessary tables from the ISO standard which we will need. And using this process, you should be able to perform the calculation. So now we could do so that that you will start the calculation, and then we can continue and finalize it next week. This presentation slide set is available in the Moodle, and I would advise to learn to use MathCAD at this point. So you can start the calculation, and if you need any help, I'm here to help you, and we can I can guide you through breakout rooms, so I can divide you into individual rooms and then give you guidance if you need. Okay, so feel free to start.
Excuse me, sir. May
Yes.
I ask you a question about the final exam for this course?
Yes, sure.
Well, my question is what will be the how to say that? Well, I wanted to ask if the exam will consist of some theoretical questions or tasks like this with calculation.
There will be both. It's machine elements is quite much calculation, so there will be several calculation tasks, but also there will be some, probably at least one essay task in which I ask, for example, I will show you a picture of a bearing system, and then I ask your opinion about it and maybe ways to improve it. And in addition, there will be some selection tasks. So select the right option, select the incorrect option, that kind of tasks. And the exam will be a Moodle exam, and at the end of April, and it will be held in the classroom. So there will be a computer classroom where you enter, and you have a possibility to use all the Moodle material I've shown. You have the possibility to use any online calculators from the internet that you can find. You can bring all the library you can find. You can bring in tons of books if you need and seem it necessary. And also you can use MathCAD as a calculator. But for the calculations, I will require that you do the calculation on the paper as well. So then I get your handwritten calculation, and if you didn't score the full points in the Moodle result, then I can go back onto your handwritten calculation and see where's the problem, and if some points could be granted.
Okay, I see. Thank you. Thank you very much.
Uh, excuse me.
Yes, go ahead.
I wonder which outer diameter should I use, the 7 millimeter or 100 millimeter?
For which?
The hub. I will share my screen.
You mean this DHO?
Yeah.
Yeah, that's a good question. What would you think? Should it be 100 or 70?
I think it should be 70.
Mhm.
Because most of the length is for 70.
Yeah, that's a good argument, and I use the same for the same reason. Of course, you could use the 100, but then you would, if you would use the 100, you would overestimate the rigidity of the hub because most of the part it's 70. So 70 is a good option.
And should I make the should I calculate mm, the number between 70 and 100?
Yeah, if you would want to do it really precise, you could do that as well. I use 70 for DHO.
Yeah. Thank you.
You're welcome.
So if we speak again about outer diameter, we don't need to calculate any tolerances for this. We just take 70. And we agree?
You will need to consider tolerances for this shaft and hub for 44.5 millimeters. There are tolerances to that, but regarding the DHO, which is the outside diameter of the hub, there you can only use the nominal. There's not actually even tolerance given for the 70 millimeters.
Oh, right. Yeah. Okay, thank you.
Okay, now I put into the Moodle page the end results for maximum torque and the minimum torque, and also for the minimum hub temperature. So you can verify your calculation against those. Okay, so time is up for today. So let's continue next week. I did put into the Moodle the results, so you can verify against that. Next week we are going to briefly look at the main results, not to go detailed about the calculation, but to see what is the main steps and why are the results as they are. Okay, see you next week.
See you. Bye.
Thank
Bye
you,
for the
bye.
lecture.